Hello everyone. Let's see how to solve this question. Topological sort using DFS. Okay. First of all, let's see what is the definition of topological sort. Uh, Topological sorting for directed acyclic graph is a linear ordering of vertices such that for every directed edge u to v, vertex u comes before v in the order. Yeah, I'll explain you this with an example. So, what are the asking is we'll be given a directed acyclic graph. And by directed acyclic graph, that also I'll explain, and we need to return the order of vertices using topological sort. Okay. Will be given edges, the edges, the number of vertices, and we need to return the order. So let's see. Okay, what is this topological sort? See here, see this graph. This is a directed graph, and there is no cycles in it. We can form, we can give the topological sort order for this. But what is the problem if it is an undirected graph or if it contains circle? Let's see that first. Okay. See, let's take an example. I have an undirected graph. So 0 and there is 1. So now tell me the order which comes first. Will 0 come first or 1 come first? We cannot say. There is no pointing. 0 is not pointing to 1, 1 is not pointing to, both are pointing to each other. There is no single direction. So we cannot give order for this undirected graph. That's why they said directed graph. And why did they say acyclic? Let's see again with an example. Assume there is a graph like this, 0 to 1, again 1 to 2, and 2 to 0. Okay. We need to give the order. Okay. See 0, 1. So I'll keep 0, 1, 0, comma 1, 1 to 2, 0, comma 1, comma 2. This looks okay. This looks okay. But there's a problem here. 2 to 0. Okay, it is we have 0 1 2, and again we have 2 to 0. It is not following the order. I'll explain you here. So we have 0 1, it satisfies this, and 1 to 2, this is also okay. But we have 2 to 0, which we cannot satisfy. If I keep 2 to 0, 1 to 2 is satisfied, 2 to 0 is satisfied, but 0 to 1 is not satisfied. So if there is a cycle, then definitely we cannot apply this topological set. Cannot have an order. That's what they said. Uh, DAG, directed acyclic graph. Okay. I'll erase this. So this is an example order. If you see what are the edges we have, these are 1, 2, 3, 4, 6 edges. Let's see if this order satisfies that. 5 to 0. 5 should be before 0. And here we have 5 here, 0 here. So, and 2 to 3. 2 should be before 3. I have 2 here, 3 here. Similarly, if you check this for all the edges, it will follow that order. So this is one of the possible topological sort order. There can be other possibilities also. This is one of the possible. We need to return this order. Let's see how can we solve this. Okay. Hmm. I'll apply simple DFS with a slight modification. Okay. Let's take visited array. How many edges? How many vertices? 6. Okay. Now visited array. So now what I'll do is I'll check for all the edges, all the vertices, whether they are visited or not. And see, I'll maintain a stack. So this will be my front. Okay, n will be my friend. Think of it in that way. Okay, my friend will be at the end. So I'll go to 0. I'll check its neighbors. Are there any neighbors? No, there are no neighbors for 0. So this, so I'll keep stack and I'll keep it here. Or else, isn't this as my friend element? That would be better. My friend is here. So keep it as post 0. Then I'll go to 1. So 1, I'll mark 0 as visited. I'll go to 1. I'll check its neighbors. What are the 1 neighbors? There are no neighbors for it. So I'll mark it as visited. I'll keep it in stack. I'll check for 2. So what are the neighbors of 2? 3. Now what I'll do is I'll mark 2 as visited and I'll go to 3. So and I'll mark 3 as visited and I'll check its edges. What are the edges? 1. Okay, 3 edges 1. I'll come to 1. It is visited and I'll come back. I'll come back to 3 and I'll go check for another. What are the other neighbors of 3? 1 is done. So there are no neighbors. What I'll do is I visited all the neighbors of 3. Now I'll keep it in stack. So 3 and is all neighbors are visited. Now I'll come back to 2 and check its other neighbors. So 3 is the only neighbor that is finished. So I'll keep 2 now. Okay. So 0, 1, 2 is I have started, done. I'll go to 3. I'll check. So it's revisited, it is visited. So I'll go to 4 and I'll check its neighbors. What are the neighbors of 4? I'll mark 4 as visited and I'll check its neighbors. What are the neighbors? 0. Is 0 visited? I'll come back. I'll come back to 4 and go to the neighbor. What is the other neighbor? 1. Is 1 visited? It is visited. I'll come back to 4 and I'll check other neighbors. What is the other neighbors? There are no other neighbors. I have visited all the neighbors. So all the neighbors of 4 are visited. Okay, 4 in my stack. Next is let's check 5. So what are the neighbors of 5? 0 and 2. I'll check 0 and 2. Okay, 0 visited, it is visited. Come back to 5 and I'll go to 2. Is 2 visited? It is visited. I'll come back to 5. All of the 5 neighbors are visited. Oh, I forgot to visited. Are visited. My gauge is 5. Okay, so my result will be simply reverse of stack, just reverse it. So which will be 5, 4, 2, 3, 1, 0. So if you observe, I got my answer. So and I'll explain why this worked. So what are we doing? So we went to a node and we visited all of its neighbors. Then we are keeping this in our stack. Okay, that means uh, so, think of it as like let's check for 2, 3. So okay, um, so there's an edge between 2 and 3. What I am doing is I'm not keeping 2 first. I'm checking its neighbors, which is 3. There's an edge from 2 to 3. I'm checking again its neighbors. So these neighbors. So after visiting all the neighbors of 3, I'm keeping 3. After that, I'm keeping 2. That means, so at the end, I'm reversing. So I'm having 2 first in my answer. After that, I'm having 3. So that means I have visited all the neighbors of 3. I'm keeping 3. So 3 is one of the neighbors of 2 and I'm visiting all the neighbors of 2 and I'm then keeping 2. That means uh, all the vertices that are being pointed by 2 will come after 2 only. With the dry run we have done. Let's see how can we write code for this. Okay, so it's simple DFS. So what do we want? A boolean visited. A result, a stack. Now go to every node, see if it is visited or not. If it is not visited, so apply DFS on it. And what do we say? What is the current node? So I need to prepare adjacency list. I forgot it. Let's prepare that. So I'll have V nodes and V number of vertices. So let's start add up array list. So let's visit each edge, insert them. So my U will be of 0, my V will be E of 1. So I have an edge from U to V. Get of U. So I have my adjacency list prepared. So what do we have saying? So the current node visited, the stack, and what else? And the adjacency list, and the number of nodes, number of vertices. So this will return my store the result in stack. After that, I just need to reverse the stack. Okay, I take a position. So the top element should be at first, right? So I'll do this. While stack is not empty, while it is not empty, I'll pop the top element. I'll add it to result. And I'll return result. Okay. Let's write DFS code. So what do I have? A node, a boolean listed array. So stack so the stack and adjacency list. Okay. And number of vertices. So I got all. What I need to do is I'll mark the current one as listed first. List of node. So I need to check all of its neighbors. So I need to check if it is visited or not. If it is not visited, visited of neighbor, I'll do DFS. DFS of neighbor, visited, stack, adjacency list, and the vertices. Okay. Similarly, if it goes to another neighbor to do DFS, after completing, after visiting all the nodes of a neighbor, I add it in the stack. Okay. So yeah, let's see. This is running fine or not. So we got another stack error non-static method. So this is a static method. Okay. Cool. Okay. Let's submit this. So this is POD for today. Okay. So now let's analyze time and space complexity. So what will be the time? So let's analyze time. So I'm ignoring time for adjacency list. If you want, you can explain that too. So what are the other things? This is big of V. This is again big of V. And DFS in a directed graph, it is again big of V. Big of 3. Big of V equivalent to space. Let's see. Again, I'm not explaining about the adjacency list. I'm not considering that. What are the other? A visited, a result, and a stack. This each consumes big of V and recursive stack space big of 4 into including recursive stack space, which is almost equivalent to big of. Yeah, and that's it. Thank you.